Exercise 22. A block S of mass 2 kilograms is pulled along a horizontal frictionless rail with a horizontal force F of magnitude F equal 10 Newton. At t equals 0 seconds, S is initially at rest and the position of its center of mass coincides with the origin. Take G equal 10 meter per second squared. Now name and represent the forces acting on us. The forces acting on us are the weight, the normal reaction of support, and this applied force, the F vector. Now to represent them, as long as we're dealing now with as a block of mass m equal 2 kilograms, we can consider this object to be a point or a particle object or a point object. And that's why, given that its center of mass initially coincides with the origin, then we can consider this object to be starting at the origin. Now, concerning the representation of forces, in the previous classes, when you were asked to represent the forces, if it was a contact force, then you had to represent it at the point of contact, weight at the center of gravity, and so on. Now, when dealing with summation of forces in Newton's first law and second law, we need to translate all these forces on one point, which represents the particle, to be able to add them up to each other. So now I'm going to represent them on one point. Okay, the normal reaction of support is upwards, the weight is downwards, and the applied force is horizontal. But here I want to note something. Sometimes you will not be evaluated for the length of the vector, but in this case you will, because you are given the magnitude of F and you are given the mass. Okay, so you can calculate the weight from the mass m times g 2 times 10, which is 20 Newton, and you have 10 Newton in F, and you know that the body is at equilibrium on the y-axis. It's neither moving upwards nor downwards, so this means all the upward forces are equal in magnitude to all the downward forces, and the only upward force is the normal reaction of support, and the only downward force is the weight. So here the length of the vectors n and w must be equal to each other, and we already calculated the weight to be 20 Newton, which is double F. So if you draw this one to be 4 centimeter, F must be 2 centimeter, and W must be 4 centimeter. Using a scale, for example, every 1 centimeter equals 5 Newton. Alright, so here I'm showing that at equilibrium along y-axis, N equal W in magnitude. That's why the length of the vectors must be equal here. Now determine the acceleration of the block, then deduce the nature of the motion. Summation of external forces is equal to ma vector by Newton's second law. W vector plus n vector plus F vector equal ma vector. Projection along x-axis. We have F external F on the x component of the external forces is equal to ma. The horizontal force here is plus F because it's in the positive direction, equal ma, then a equal F over m, 10 Newton over 2 kilograms, 5 Newton over kilogram, 5 meter per second squared. Now, one of the students asked me, why do we directly say that Newton per kilogram is equivalent to meter per second squared? I explained this by referring to the definition of the acceleration. When we first defined the acceleration in the previous lesson, we said that it's equal to the difference or the variation in the velocity with respect to time. So it was meter per second over second and meter per second squared. Now, according to Newton's second law, the summation of F vector is equal ma vector, then a is F over m. So in this case, it's Newton per kilogram. That's why we consider that we can consider that Newton per kilogram is equal to meter per second squared. Okay. So here, determine the acceleration to introduce the nature of motion. Since a is positive and the trajectory is a straight line, then the motion is UARM. Why UARM? Because a positive, and rectilinear motion because it's moving along a straight pathway or along a straight line. So part 3, determine the magnitude of the force exerted by the rail on us. One of the students thought that the force exerted by the rail on the us is the friction, but we are given that it's a frictionless. It's not only the friction, which is the possible force that could be exerted by the rail on us. Simply here we have us is not moving vertically due to the normal reaction of support exerted by the rail on us. So this is the force they're asking us about. Alright. So the force exerted by the rail on us is the normal reaction of support in this case. Otherwise, us would have fallen down vertically under the effect of the weight. But because there is normal reaction of support opposing the weight, that's why opposing it in the same manner, with the same magnitude, that's why us remains at equilibrium vertically. Now the force exerted by the rail on us is the normal reaction of support. S is at equilibrium, not moving along y-axis. Then the summation of all the y components of the forces is equal to 0. We have N is upwards, W is downwards, so we write plus N minus W equals 0 when we project. N minus mg equals 0. Move mg to the other side, it becomes N equals mg 2 kilograms times 10 Newton per kilogram, which is equal to 20 Newton. Okay. Now find the expression or the position time equation and the speed time equation of motion of S. Because we already proved that it's UARM, then x equal half at squared plus v naught t plus x naught. A is calculated to be 5 in part 2. V naught is 0 because we were given that the object was initially at rest, and x naught because we were given also that initially the center of the mass coincides with the origin of the axis. So it's 2.5 t squared SI unit. V equal now AT plus V naught, same thing here. So 5t plus 0 is 5t, also in the SI unit. I'm explaining here that x naught is 0 meters since the position of its center of mass coincides with the origin, and V naught equals 0 meter per second since S was initially at rest. Finally, calculate the distance covered and the speed of S at t equals 3 seconds. So go back to the rule, t equals 2.5 t squared, which is x minus x naught, and 2.5 times 3 squared is 22.5 meters, and the speed v is 5t, 5 times 3, 15 meters per second.